I'm very excited to be staying at Carnegie as the next director. It's an exciting time, as you've heard in the last couple talks, with our Magellan telescopes working great and our Giant Magellan Telescope moving forward. Tonight, you're going to hear from the other really exciting component of our Carnegie program, which you may not have heard about too much, except for Andrew last year, I guess, and that is our theoretical component. For the first 100 years, the observatory really relied on people like myself, observers who go to telescopes and take images and take spectroscopy and try to interpret it. The difficult thing is to really interpret such data, one really needs a theoretical base. And so the observatories for a long time had been hoping to start a theory program here in Pasadena. And in 2006, I think it was, I met tonight's speaker for the first time, and I interviewed her with Wendy Friedman, our previous director, who all of you know really well. And after we interviewed Juna, I turned to Wendy and said, we are going to hire her on our staff. And that is exactly what happened. Actually, about a year and a half later, she didn't even get to complete her postdoc, and we jumped at the opportunity to hire her on our permanent scientific staff. And those of you who saw her talk a few years ago will know why. And those of you who will see her talk now will know why. Juna's really a very incredible, broad theorist. The great thing to me is that she works on all topics, everything from the intergalactic medium to galactic structure to black holes, which is the topic of tonight's talk. And I see it's a very popular topic. We always draw a full crowd when we talk about black holes, and so you'll leave tonight knowing a lot more about black holes. But the one thing I do really want to emphasize is that when Juna came in 2006, she was the first theorist in 100 years we had hired, and I think we at the moment have 7 or 8. And so the program has really grown over the last 7 or 8 years. Andrew was the second permanent hire we made on our staff, and now we have a bunch of great young postdocs who you'll be hearing from in the next few years. And so Juna really gets a lot of credit for coming out on a limb, so to speak, and going to an observatory where there were no theorists and starting a program. And the program is really thriving, and it's one of the most exciting things about being at Carnegie right now. So, and I think you'll understand why in the next few minutes. So help me welcome Juna Kollmeier to the stage.
Thank you very much. So it's a pleasure to be here. How about those guitarists? Can we clap again for those? Since we weren't allowed to clap all 4 times, even though we all wanted to. So tonight we're going to talk about the edge of reason, the black holes in our universe. So first, I must apologize to all of you who are coming expecting a talk about this very popular At the Edge of Reason, Bridget Jones' diary, movie. We're not going to be talking about that, okay? Our talk is going to go more like this. I think you'll agree, though, I think Renee Zellweger was really experimenting with space-time in her limited way there. Okay, so what are we going to talk about? So first, edge. Let's just define a few things. So I want to be very clear at the outset. Black holes, our struggle to understand them, really constitute the very, very limits of our understanding as a species, okay? This is the limit. So if someone tells you they really understand black holes, with almost no exceptions, they are lying to you, okay? So the edge, the line or part where an object or an area begins or ends. And of course, reason, a statement or fact that explains why something is the way it is, and the power of the mind to think and understand in a logical way. So tonight, I'm going to talk a little bit about the facts we know about black holes. The first part of my talk will be concerned with these facts. And the second part will be concerned with really this other aspect of reason and the power of the mind to really figure these things out. Hopefully by the end of the talk, you'll need a stiff drink and a quiet place to absorb what I've tried to tell you. So what is a black hole? So first, why black, why hole? So a hole, because it's a mathematical singularity. So this was a point where the density is infinite, where space-time is infinitely curved, a point with infinite mass and 0 volume. And this first solution to Einstein's general relativity came about in 1916 by Carl Schwarzschild. I'll talk about that in a little bit. But that's why it's called a hole, and I'll show that to you in a second. Black, because light is absorbed, it's not really absorbed, but it can't escape, at what's called the event horizon, again associated with Schwarzschild. This is very similar to a black body, a perfect absorber radiator in thermodynamics. And so that's why it's called a black hole. And of course, you've heard this a million times, but even light cannot escape the gravitational pull of a black hole. So you've heard that many times. Let's go over some of this. So this is where this notion of a hole comes from. So this is a sort of schematic picture of space-time. Of course, you can't see the time dimension here. But you can see once you have something with very, very high mass in a very, very tiny area, just mathematically what that looks like is singularity, this point that goes to 0 volume. And so people call this sort of, I mean, it looks kind of like a hole, right? Now, if there's one thing I want you to take away from this talk, is that what I think the really defining characteristic of a black hole is, it's an object with no surface. Okay? So for the purposes of this talk, I'm going to define a black hole as an event horizon without a surface. And I'll talk about what an event horizon is. So I just want you to think about that for a second. So you're sitting in a chair with a surface, and you can close your eyes with the surface of your eyelids, and you can use your brain with its surface, okay? There is nothing in our everyday experience that doesn't have a surface, okay? Now you're thinking, well, you know, it's a black hole is a really, really massive thing in a really, really small area. It's got high density, and there are other weird things that have high density, like neutron stars. So a neutron star has a mass of about the mass of the sun, and it's basically in something that has 12 miles in diameter, so something from here to Burbank. So that's really massive, that's really dense, that's a weird thing, okay? But this is just a really extreme version of things you understand, like soccer balls and bocce balls and medicine balls. You kind of get that. It's just the extreme end of what you get. No, black holes are not like this. So these are just not like weird versions of regular stuff that you interact with, okay? We have no everyday experience with these things, nothing. Okay, so I think that's clear. So astronomers have been grappling with black holes theoretically for hundreds of years. Okay, so they came from the imagination of a few individuals and out of mathematics, and for hundreds of years we've been sort of toying with these ideas. But it's only over the last 100 years that we've been able to make some headway into actually confronting these theoretical ideas with observations. Okay? So I want to just stress we are at a very, very, very special time in the history of humanity to have this opportunity to be here when we're actually confronting these theoretical ideas that we've been struggling with for hundreds and hundreds of years with actual data. Okay, so I told you I was going to talk about the facts. So in the spirit of Friday, let's just, many of you guys are thinking, okay, what do we know? Just tell me what we know. So let's get on with it. So there are 3 basic parameters that define a black hole: mass, spin, and charge. Okay, this is a part of what's called the no-hair conjecture, that these 3 quantities perfectly specify a black hole mathematically, and there are no other quantities that you need to measure. So far, we've been really good at measuring this first one, mass, which is amazing. We're starting to get some clues as to how to measure spin. And we're nowhere near measuring charge. Okay, so really it's this first one that we're focusing on. Fact: there's at least 2 regimes of astrophysical black holes. There are stellar mass black holes. These are normal black holes. And the way you get a stellar mass black hole is you got a star that's a bit bigger than our sun. And at the end of its lifetime, it will explode, either depending on exactly how massive it is and what type of configuration it is. It will leave a remnant that's about as massive as the sun, and it'll be a black hole remnant depending on exactly how that star dies. And so we can calculate that these stellar mass black holes are a result of supernova explosions, supernova of different types. And we can measure these things. We can see these systems when they accrete material. So we know about them. They exist all over our galaxy. Okay? The other type of black hole that we know about are what's called supermassive black holes. Now, these are much more confusing. And they're confusing because we don't know how they formed. Okay? We have some ideas, but we don't actually know how they formed. Unlike stellar mass black holes, where there's a pretty good theory worked out about how you actually get a stellar mass black hole at the end of a star's lifetime, we're just really grasping at different ideas for how to form a supermassive black hole. And these black holes can be 10,000 to 10 billion times the mass of the sun. Okay, so these things are huge. Now, if you wanted to take all the black holes and line them up by mass, and like a way I thought we could do that is, I don't know if any of you look at these superheroes and stuff. I know that there are some people who might be interested in this. If you line up all the superheroes by how big they are, from Marvel actually, you got Ant-Man and Howard the Duck on the sort of small side. And then you've got these big guys like Hulk, okay, and Iron Man on the sort of big, massive side. So if this were translated into black holes, basically we've got the Howard the Ducks and we've got the Hulks. But we actually haven't seen much in between. Now, in principle, you should definitely have like Wolverine and all these other guys, like for sure, they should be there. There's no reason why that continuum of black hole masses shouldn't actually exist. But in fact, we haven't observed them yet. There are some candidates. There are some candidates sort of in this range, but we haven't seen them yet. So we've seen black holes between 1 and 100 times the mass of the sun, and we've seen black holes between 10,000 and 10 billion times the mass of the sun. But we don't know what's going on in the middle, and that's one of the big outstanding questions in astrophysics. Black holes can feed. So normally when we think of black holes, we think of these cosmic vacuum cleaners that are just sucking up everything in their gravitational grip, right? And that's a very common, even light can't escape, right? But in fact, when they feed, they shine. And they shine as a quasar. And I'll go over at the end of the talk how we figured that out. But an accreting supermassive black hole will form what's called an accretion disk. That's a disk of gas, and due to its angular momentum, it forms a disk around this supermassive black hole. And when that gas accretes onto that central supermassive black hole, it actually emits light. It actually emits light all throughout this accretion disk. And we can make accurate predictions for what that gas should look like, and we can compare that to observations of what are called quasars and active galactic nuclei, and in fact, they agree. So we know that when black holes are feeding in this mode, that they shine, and we know how they should shine. We know what wavelengths they should shine, how that energy should be distributed. And in fact, for many decades, this was the only way we knew that there had to be supermassive black holes out there, because we saw these things feeding, we saw these things shining with energies that you can't explain any other way, okay? So of course, black holes can be active. Here I'm showing a supermassive black hole in a nearby galaxy, and this is the radio jet emission that comes from that system. And in fact, one thing to note is that when these things feed, when they feed a lot, they're very, very bright, and that's something known as a quasar, quasi-stellar object, because it looks like a star, but a star that, we don't have anything like that in our galaxy, a star that's emitting so much energy that it's outshining an entire galaxy by itself. And the era of these quasars, I'm showing this figure here, and what basically it's showing is on this y-axis, it's just showing the density of these big quasars. And on the x-axis, it's just showing time. So 0 is today, and over here is a few 100 million years ago, okay? And you see that right now, there's very few bright quasars actively feeding. But in the past, there were a lot more. So it means that the era of quasars is over, and it happened when the universe was around a few billion years old. That was this peak in the sort of era of black hole feeding. So now we know that most black holes are dormant. So they're not feeding actively. They're sitting in the centers of galaxies, and we think they're everywhere. We think they're in big galaxies. We think they're in little galaxies. Whenever we go to measure them in these big galaxies, we seem to see something that tells us that there's a black hole there. But we know most of them now are not feeding at very, very high rates. Most of them are sort of, snacking every now and again. Okay? But there are still some pretty powerful ones nearby, so that's good. So we think they're everywhere, and I think one of the most exciting things is, there's the one at the center of our galaxy. So what I'm showing here is an actual picture of the center of our galaxy, the Milky Way galaxy. This star represents the actual center of the galaxy, and these little bullseyes are actually infrared measurements of stars, okay? And so these infrared measurements are showing you the locations of stars, and this is a picture from 1995. Okay, and this thing's gonna go in time. As people monitored the center of the galaxy, they could watch these stars move. And this movie is gonna go all the way to 2013. This comes from the UCLA Galactic Center group that's led by Andrea Ghez over at UCLA down the freeway ways. And so this is this is extremely exciting because now we can watch these stars move in orbits around what looks like nothing. Okay, now we have to take a detour into gravity because that's the key to our story. So we know that the attractive force of gravity gets stronger the closer you get to an object, of course. So this is just an exaggerated version of a planet going around the sun, a planet like the Earth. And we know from Kepler and of course Newton that the force of gravity is proportional to the masses over the distance squared. Okay? And I'm not going to apologize for showing you guys any equations. You guys do math every day. Okay? I'm not going to show you anything I'm not going to make you calculate anything right now, but these equations are something that you can understand. And so never be intimidated by equations. They're very, very liberating. Anyway, so the closer you get to an object, the stronger that force of gravity. And Kepler figured out that you could figure out the mass of something like the sun if you knew the motions of an object orbiting it. And that very same principle applies here. We see stars in Keplerian orbits around a dark center of the galaxy. So it's really, really important to look at this picture and realize the implications of this, and in particular this star, which is an awesome star, because it goes around, it closes the loop on its orbit, which means that just the way you can measure the mass of the sun from knowing the orbits of the planets, you can measure the mass of that dark thing by knowing the orbits of these stars. And I think it's also important for us here to think about how lucky we are. So right now, you are just sitting a few miles away from the place where the people who made these measurements sit and do their work. You can go to sit on one of Andrea Gez's talks if you want. That's really exciting. You don't have that many moments in the history of the universe where you're so close to such an important measurement. But the key to this measurement is that it tells you that there's something about 4 million times the mass of the sun in the center of the Milky Way. And you can't see it. It doesn't give off a huge amount of radiation like a quasar. And in fact, the most recent thing that people have measured was that there's no surface. So this is a new observation from something called the Event Horizon Telescope, where they use very, very precise radio measurements to actually locate the size of the inner orbits around a supermassive black hole. This is the closest in that you can get. And I'm just showing this graph. This is just showing the, basically the innermost stable circular orbit around a black hole as a function of black hole spin. And their measurement is this blue line. And that essentially tells you, and these are the theoretical models, and that essentially tells you black hole spin can be a parameter. I told you we don't know how to measure that yet perfectly, but it can range from 0 to 1 in these units. And what it tells you is that for these different models, we've basically gone, our measurements now go down to the innermost stable circular orbit, all the way up to black hole spins even as high as 0.6. So it means we're really getting down to the centers of these systems, and we're really seeing there's no light being emitted from this innermost stable circular orbit, and that means there's no surface. Because if there was a surface, like a neutron star, you would see stuff crashing into that and thermalizing and giving off radiation, and they don't see it. So that means there is no surface. So this is a very, very recent measurement. And most recently, in fact, only a few weeks ago, they made a similar measurement in another galaxy. This is for our galaxy, for the supermassive black hole in the center of our galaxy. And this is just so incredible that not only, that we're actually probing this event horizon. And this is something that the Event Horizon Telescope is allowing us to do. So going back to Joe Friday, those are some facts. And I want you to remember facts. But I think it's also important to understand, how did we come to know anything about these objects, about black holes? So, so what are the facts, and where did they come from? So we're going to go through some of the history of how we found out about black holes, because it wasn't like this, okay? So in general, science doesn't work like this. It would be so great if you just had to climb up to the top of Mount Wilson and there are the facts. But it doesn't. So scientists are not priests, not magical, and definitely not divine, although I know some of my colleagues act that way. I'm sorry. I know. Okay. It's a lot more like this. Okay? It's a lot more like mining the universe for its secrets. And the universe does not want to give you those secrets. So you have to sit there in the grime for years and years and years and years and years, and maybe you'll never find anything, but maybe you find gold, right? So I want to go over some of how we came to know what we know about these objects. So here's our gold mining timeline. This is up to 1900, okay? So you start with Johannes Kepler. And Kepler, Newton gets all the credit for early gravity, but Kepler was really an amazing, amazing individual. For measuring the precise motions of the planets, he was basically able to figure out the universal laws of gravitation, although he didn't cast them in as clear a way as Isaac Newton did. But he does this in 1609, okay? Newton's Principia comes out in 1687. 1781, Immanuel Kant publishes a Critique of Pure Reason, and we'll get back to that. And in 1784, this is the Enlightenment period. In 1784, this guy, the Reverend John Mitchell, he basically invents astrophysical black holes just from reasoning using escape velocity arguments, which I'll go through. And Laplace had similar reasoning. She called them dark stars, and this is in 1795. So there's this incredible burst of Enlightenment thinking in the 1780s and 90s that really set the stage for what people would then be struggling later. And of course, we got to go back to gravity, because that's the key to our story. Here is the Newtonian version of gravity that I showed you earlier. And of course, here's Einstein's general relativistic version. There's not going to be a test, don't worry. But this is, most of the time it's even easier, because you put C in terms of, you make all of these units 1, and then this gets really simple. But anyway, don't be intimidated by these equations. They're not that scary. But back to gravity. Again, when I showed this figure before, the attractive force of gravity gets stronger when an object gets closer, and it gets stronger when an object gets more massive, right? So how did this John Mitchell guy come up with the idea of black holes? Well, there was an observer, Sir William Herschel, who had just built what was then a pretty impressive telescope. It was 40 feet high, which is very impressive, and a 50-inch diameter mirror, which at that time was quite impressive. And he is observing stars, and he's seeing that some of these stars are in binaries. So John Mitchell is like, binaries, that's great, because now I can start measuring masses, and I can start measuring distances, because I've got gravity on my side. This is now 100 years after Principia, right? So he's just totally mastered Newton's laws, and he's thinking about these binary stars that Herschel is observing, and he's thinking about what to do with them. And he's just really inspired, okay? And so he's thinking, if I wanted to measure the masses of these objects, well, how would light be affected if stars were in binaries? And how would that actually affect my measurements? And he's reasoning in terms of this escape velocity. So this is the equation for the escape velocity from an object. It's just the square root of twice the gravitational constant times the mass over the radius. And we know about escape velocity because our everyday experience tells us about escape velocity because we sit on the Earth and we don't fly off it, and we occasionally watch rockets get off the Earth, right? And so if you want to escape the Earth's gravity, you need a rocket, and you need to get to 11 kilometers a second. That's about the escape speed of the Earth, which is about 25,000 miles per hour. It's pretty fast. We know rockets are powerful, right? And so in reasoning about this, John Mitchell starts to think, well, what if something was so massive that even light, which is going at a certain speed, couldn't get out of it? So let's just, the significant events of 1784. So if you go to Wikipedia and you type in any year, it'll tell you all the things that happened that year. Except it doesn't tell you all the things, it just tells you some selection of things. And so Wikipedia says, well, first it's the end of the American Revolutionary War, so that's good. King Carlos III of the Spanish Empire authorizes land grants in Alta California, so that's relevant to us. Benjamin Franklin tries to get people to alter their clocks, the French to alter their clocks in winter so that they could take advantage of daylight savings, and also invents bifocals. So Franklin was busy this year. Gauss just pioneers the field of summation with this formula, and he's 7 years old. 7, okay? But what's not mentioned is that on November 27th, black holes first appear in the scientific literature. And I've just taken an excerpt for you. This is from 1784. This is from John Mitchell's actual publication. So the S's look like F's in parts. But if there should really exist in nature any bodies whose density is not less than that of the sun and whose diameters are more than 500 times the diameter of the sun, since their light could not arrive at us, or if there should exist any other bodies of a somewhat smaller size which are not naturally luminous, of the existence of bodies under either of these circumstances, we could have no information from sight. Yet, if any other luminous bodies happen to revolve about them, we might still, perhaps from the motions of these revolving bodies infer the existence of the central ones with some degree of probability. So Mitchell is just like, what you guys need to do is go and get an infrared telescope and point it at the galactic center and measure the mass of the supermassive black hole at the galactic center. This is in 1784. This is just from this guy's mind. It's incredible. And it's not really incredible. It's just that he's sitting down with Newton's equations, which I've shown you, which all of you can, sit and struggle with, and he's thinking about how would it really work, just following that to its natural conclusion. Now, in 1795, you have Laplace, who, in his French essay, Exposition du système du monde, postulates dark stars. And he says, a star of the same density as the Earth with the diameter, which is 200 times bigger than the sun, would not let, because of its gravitational attraction, any rays of light come toward us. That's basically what he says in French. So this, at the same time, you can see these are these Enlightenment thinkers who are just struggling with, just the implications of what gravity means. That's all they're doing. And then you've got Kant. So this guy, one of the most amazing philosophers of all time. So he basically, in his work, A Critique of Pure Reason, he postulates that space and time do not actually exist. They are not real things, okay? They are just manifestations of your own awareness. And that they're just constructs that we invent, essentially, that our minds invent to organize sort of the events of our time and our perceptions. And he had this concept of the manifold of appearances. So you've got these guys on one side who are just taking all of the sort of logical conclusions of the math to their final, this is what this must imply. And then you've got Kant that's like, he's thinking, guys, you're just in some big hallucination, essentially. So it takes hundreds of years to resolve this, and I will get back to Kant. Now, of course, the 20th century was an incredible scientific time. So it starts, and that story, again, starts in Pasadena, okay? Starts at Mount Wilson. So you've got Fath, who's up at Mount Wilson, taking spectra for the first time. Of course, you've got Einstein and general relativity being invented, and Carl Schwarzschild solving Einstein's equations, which he couldn't quite do. You've got Karl Jansky, who discovers the radio signature from the galactic center, which is the signpost that there's something there. You've got the invention by Groth-Reber, and I'll go through all these in more detail, of radio detection. You've got Martin Schmidt figuring out that these quasars are actually at large distances, which means their energies are ridiculously high. And then you have people like Ed Salpeter and Don Lyndon Bell that trying to figure out how do you get those types of energies out of astrophysical sources. You also have in the 70s the Bekenstein-Hawking radiation. I'm not going to talk too much about this alternate view of black holes. It's fascinating, and there's a lot of really great work that's currently being done on this. But I'm going to stick to the astrophysical side of things. And of course, in 2004, you have Andrea Ghez at UCLA and Reinhard Genzel in Germany basically measuring simultaneously from different telescopes the orbits of stars around Sagittarius star, thus confirming the existence of a supermassive black hole without doubt. And of course, we've just had in 2012 this measurement by the Event Horizon Telescope that this thing doesn't have a surface. Okay, so that's where we are. And this is where we come in 100 years. So let's just kind of go through some of that. So in 1909, you have people invent, they're dealing with what's called spectroscopy. So they're breaking up white light, the light from all the objects in the universe, into its constituent parts and looking at the distribution of energies at different wavelengths from these astrophysical objects. And Fath was the first to do this at Mount Wilson. And what he discovers, kind of to his amazement, he takes a spectrum of something like the Andromeda galaxy, and then he takes a spectrum of another type of galaxy, and he finds some of these nebulae. Now, at this point, they don't know if the galaxies are, if these external, they're called spiral nebulae at this time. People don't know if they're internal to our Milky Way or external to our Milky Way. We have no idea what the size of the Milky Way is. There are lots of debates raging at this period. But anyway, he takes spectra of the Andromeda galaxy, and this is just a spectrum. This is just the intensity as a function of wavelength or of energy. And some of these galaxies look very similar to stars. They look like a big collection of stars. And some of these galaxies that he takes spectra of, they don't look like that at all. They look very, very different. They look more like planetary nebulae. They've got different types of lines, and you can see, you don't need to be a spectroscopist to know that that doesn't look like that. And that's what he basically figured out. And of course, in 1909 and 1910 through 1915, the theoretical world is just being completely liberated by Albert Einstein and his special and general relativity. And this is actually a picture of Albert Einstein visiting Carnegie in Pasadena. This is from 1930s, slightly later. And of course, he was there to talk to Hubble about the cosmic expansion. But of course, people in Pasadena were very interested in Einstein's general theory of relativity. In fact, some of the early tests using the solar eclipses were performed by Carnegie astronomers. They didn't come to the right conclusion, though. That was Eddington. And of course, in 1916, you've got this guy, Carl Schwarzschild, who actually solves Einstein's general field equations. And he comes up with the Schwarzschild radius. So this is an exact solution of general relativity. And it basically tells you what this event horizon, what is this limit where you can't, where light cannot escape from the pull of the black hole. And it's this very, very simple equation. You can see that the Schwarzschild radius is proportional to mass. And this is in 1916. So for an object about the mass of the sun, the Schwarzschild radius is about 3 kilometers. So not that big. For something 10 times more massive, it just goes like the mass. It's just 10 times larger. So really easy to figure out the Schwarzschild radius. So just remember that. For an object the mass of the sun, 3 kilometers is the Schwarzschild radius, and then you can figure out the Schwarzschild radius for any mass. Okay? And so in continuing and sort of people struggling with these galaxies, again, you've got Carnegie astronomer. In 1943, you've got Carl Seifert, who's up at Mount Wilson again, and he's looking at all these different types of galaxies, and I've just shown a medley here. And what he says is that, some of these galaxies are not like the other galaxies. Their centers look very different Their spectra look very, very different. And in fact, he's looking at the broad emission lines coming from the centers of these galaxies. And these emission lines are thousands of kilometers a second wide. How do you get a line that broad? What kind of dynamical entity is at play that would broaden the lines in such a way? And of course, this is the 40s. The 30s and the 40s were a pretty tough time on the world. But after World War II, there's just an explosion of radio astronomy, of course, from the expertise that people had gained during the war. And you have Karl Jansky first making measurements. This is actually a picture of one original sort of radio telescope. It was called Karl Jansky's merry-go-round, and he just used tractor tires, I believe. So it's basically an agricultural kind of device that he then mounted these radio antennae on to try to measure radio signals from the sky. And you have this radio engineer who doesn't get that much attention in the literature, but this guy was incredible. He just built a radio telescope in his backyard, a reflecting telescope. And in fact, this guy would really transform things, because he would make the first radio map of the whole sky, okay? And he called this cosmic static, right? So he was looking at the sky, at this radio emission, and he knew that this was not coming from any kind of local sources, and he basically says, from this big map, the foregoing observations confirm previous evidence that radiation in the radio spectrum is apparently coming from the direction of the Milky Way. In fact, this is basically finding, again, similar to Jansky, who discovered this radio emission from the sky. He's figuring out that the center of the galaxy emits in radio waves. But you can see this is sort of the scale of the sky, and this is the radio emission. It's like huge on the sky. I mean, this is not a local kind of point source like what we're talking about. And so one kind of side note, so there was an APJ editor at the time, Otto Struve, okay? And he couldn't find a referee for this paper, for either of these papers in 1940 or 1944, because it was too much engineering for astronomers and too much astronomy for engineers. So he just basically decided that it was better to let a bad paper through than reject a good paper, which is still the prevailing wisdom at APJ, which sometimes you have to read a lot of bad papers. But thankfully, that was the attitude that he took, because he just decided himself to let these papers into the Astrophysical Journal. But anyway, this cosmic static, they don't know, at this time, Gert Reber doesn't know exactly where it's coming from. You can see this is the whole sky. So you just have some huge emission coming from the Milky Way. And it was actually Martin Ryle who figured out how to get these radio waves to a point where you could actually localize the sources of this radiation, okay? And so he basically pioneered radio interferometry, and then was able, because you could pinpoint radio sources, you can now say which sources you could see with your eyes and with telescopes, with optical telescopes, also corresponded to radio sources. And in fact, he publishes, this leads to the publication of the third Cambridge Catalog of Radio Sources, which is a very, very important catalog of very bright radio sources and quasars. So Martin Ryle sort of focuses things, but then it gets really confusing again. And why does it get confusing? So this is from a paper by Burbage in 1959. And all through the 60s, all through the 50s and 60s, people just did not understand, now that they could connect the radio sources with the optical sources, they just did not understand how you could get the estimated energies that they were getting. These were energies, here we got in coma 4 × 10 to the 40 ergs. Just tremendous energies, and people did not understand how you could get that. And of course, by this time, we know that the galaxies are extragalactic, so we know that these are very, very high energies. We don't know exactly how far they are away, but we do know these energies are very high, okay? And Bada and Minkowski, they struggle with the jets that are produced by these quasars, these feeding objects, and their radio signature. So what you see in the middle here is what looks like a point source. Now, this is a very, very high-resolution image. Bottom and Minkowski, they had an image like this. So it just looked like some big old blob of radio emission, and then there was some big old blob of, there was optical emission as well. And then they were able to, they basically were able to connect this jet to an optical galaxy. But at this time, they had no idea how you formed these jets. So people would be struggling with how you form these jets and how you get these energies all throughout the 50s and 60s. And in fact, because these active galactic nuclei, these black holes that are feeding, because they're varying in time, so sometimes they eat a little, sometimes they eat a lot, and their energies go up and down, and that's shown here. Here's just, I'm just showing date on the y-axis. So this is just the day, the year, and this is frequency on the x-axis. So these are just different wavelengths, essentially. And the color shows you when an object is radiating a lot and when it's radiating a little. So if quasars were constant in time, then at every frequency, they would just look like a line of one color. But you can see it looks like a rainbow at all these different frequencies, which means that they're varying a lot. And by looking at the actual time signature of that variability, you can tell that the size of whatever's varying, because the speed of light is fixed, is very, very small. So now they knew that these energies were coming from this really, really small area. Now, of course, we look back now and say, well, of course, it's it's an event horizon. It's coming from the last, innermost stable orbits, and very, very close to the black hole itself. And so now we know that's small, but at the time, it was just inconceivable that you could have so much energy coming from something that small. And so 1963 is a huge year. Why is it huge? It's huge because you could suddenly figure out, there are four very important papers that come out that year. One is called The Investigation of the Radio Source 3C273. Remember, I said the third Cambridge Catalog of Galaxies? Well, this is the 273rd member of that galaxy, of that catalog of galaxies, which is a quasar. And so Hazard used this method of lunar occultations to figure out the size of this radio source. Martin Schmidt, of course, publishes 3C273, a star-like object with a very large redshift. So now we know that after Martin Schmidt's paper, people know that these things are now at cosmological distances. They're not just in the nearby neighborhood. They're very, very far away. And because they're so far away, it means their energies are even higher than people thought before. Then Bevoke has the energy distribution in the optical spectrum of 3C273. And again, we have another redshift of a radio source 3C48 by Jesse Greenstein. These are all Caltech astronomers. So of course, this gets Martin Schmidt on the cover of Time. This is a huge problem. They didn't understand how people had taken a spectrum of 3C273 and just didn't understand what they were looking at until they realized that if you redshifted the lines, it was just the hydrogen spectrum redshifted. And so it turns out that 3C273 is at about its redshift is 0.158 c, or 500 megaparsecs away, 47,000 kilometers a second receding away from us. Okay, so that means the energy associated with 3C273 is not 10 to the 40, it's 10 to the 60. Okay, and it just looks like a star. So this is just now even weirder, than anything people had been confronting. How do you get something with a luminosity way bigger than a galaxy into something the size of a star? And that's when people came up with this idea that I talked to you about earlier about accretion. So how do galaxies feed? And it was that saltpeter's notion, this is just a schematic view from his paper in 1964, showing the central singularity and then showing a flow onto that system. You notice this central part is just a circle because, as I said before, black holes have no... Awesome, good. So we know now that these massive bodies can move. They can grow in mass by slowly accreting material as it moves through this accretion disk, kind of like the way your car gets dustier as you drive in LA on the 405 at 5 o'clock. Now I want to just this 3C273, it's hard to understate what an important object this was, because it was really the focus of a lot of just intellectual, wrangling. You didn't understand how to get its energy. Where was it? How big was it? How much energy was coming out of it? And this is Lyndon Bell, and this is his commute in London. He was working at this place called Hurstmonceux Castle, and he had to commute on a road called the A273. And every time, and I'm just showing the Google Maps of how you get to his commute. But every day he would get on this road and he would just remember that 3C273 was a big thorn in the side of the thinking world, because how did you get those energies? It just seemed impossible. And his incredible realization was that you could connect these accreting objects, these high energy objects, with what was then called the Schwarzschild throats. Right? So I showed you that black hole earlier. It looks like kind of like a throat. Those are called Schwarzschild throats. And this is just an excerpt from his paper, Galactic Nuclei as Collapsed Old Quasars. And he says, we would be wrong to assume that such massive objects in space-time should be unobservable. It is my thesis that we have been observing them indirectly for many years. And he really realizes, he just connects what people are doing in the mathematical physics world with these Schwarzschild radii and Schwarzschild throats, with actually the observations that the astronomers have been struggling with, for years and years. And that's a huge, that's just an incredible intellectual advance. Now, of course, the bar is set very, very high for black holes being these active galactic nuclei. And so Lyndon Bell says, most astronomers treated this paper with silence or disbelief. Where was the evidence? Okay? Now, at that time, this accretion disk theory, this Ed Salpeter's accretion disk theory, is very young. It's very new. People don't just believe it. There's a lot of uncertainty associated with it. And in fact, there's still a lot of uncertainty associated with how you actually dissipate that angular momentum and get that gas to get down to that central supermassive black hole and actually feed it. And this just seems very counterintuitive. How can you have something small that's supposed to be black, shining brighter than galaxies? I mean, it's just like very, very, very counterintuitive. And there was just fighting about it, just straight up fighting, from the time this paper came out until the time these measurements were made. Okay? So in 1993, people didn't even think you could see curvature in the orbits at the galactic center. Infrared astronomy was in its infancy, so people had not taken telescopes and pushed them into the infrared. The atmosphere is really, really terrible to infrared photons, and so it's hard to observe them from the ground. And so in 1993, it didn't even seem possible. And in 1998, it was still very provocative to assume that stars in orbit at the center of the galaxy would be Keplerian. Okay? But because of progress in infrared astronomy, and in particular adaptive optics, many of those came from this town and the town a few miles over to the west, Westwood. Because of this progress in infrared astronomy and adaptive optics, we were able to see into the center of the galaxy and measure the orbits of not just this amazing star, S02, but several others. And in fact, with the Event Horizon Telescope, we're now this is a simulation from Avery Broderick at the Perimeter Institute of what it might look like to see a black hole as it used its gravitational field, distorted the light rays of an object behind it. So what about the future? What are the questions that we're struggling with now? So one thing that we're struggling with is, how do galaxies and black holes grow together? So a very curious relationship was observed. And it was around the year 2000 that people started really thinking there was something very fundamental to this, although it had been observed previously. And this is the relation between the size of a black hole, its mass, in these external galaxies, and the size of a galaxy. And you can see there's something that looks like a line with points clustered around it. So this very tight relationship between these two quantities. But why would a black hole at the very, very center of a galaxy that's very, very tiny know anything at all about the galaxy that surrounded it? Why would that be? It sort of indicates there's some hidden connection between these two scales, which are many orders of magnitude, 10,000 orders of magnitude, separated. And this is just a still from a simulation of two galaxies colliding and showing what galaxies colliding would look like. And if all the galaxies have black holes, then all those black holes should be colliding. And in fact, can we detect them colliding? And that's the fundamental thing we'd like to detect. We know that when black holes collide, they should emit gravitational radiation, gravitational waves. And something like the LIGO experiment or another space-based experiment called LISA, we're hoping will be able to detect those things. What about all these superheroes in the middle? Where are these guys? Where is your Wolverine? Where is your Captain America? Where are all these other black holes? They should be there. We should find them. They should be there. And as Lyndon Bell said, few, if any of us, will make a prediction only realized 200 years later. Mitchell's imagination invented black holes. We are lucky to live in an era when they have been discovered. And so now I'm just going to end with not Kant, okay? So the observations of black holes really show, it just really destroys this notion that the world is not real. It is very real. These objects emerged, they fell out of mathematics that describe the real world, maybe has a tighter correspondence to the real world than we even appreciate, and that's topic. Mathematical physics is a topic of another lecture. But these are not things that just help us organize our experiences. They bear no resemblance to our experience. We have no intuition for these things. They just come out of thought. They come out of mathematical insight and thinking about things really, really hard. And so, Kant wasn't right about this, and I strongly feel. And black holes tell us this. So, black holes in space-time, that's all I've got for you tonight. So now you can ask me whatever questions you want. And if you need to get in the covers and really try to imagine, four-dimensional gravity, then I fully endorse that.
I'm sure we have many questions. What I'd like to come up with, there's a gentleman right here in the front. Let's see.
Considering the series this year, how about dark energy and matter in black holes?
Dark energy and dark matter. So dark energy is, of course, 75% of the energy density of the universe is in this material, this matter, this dark energy, which we don't really understand what that is. It can be interpreted as in the context of Einstein's field equations for general relativity. So you can have a term in Einstein's, and of course this was what Einstein considered his big mistake. He actually originally put lambda in, which is the dark energy density, as a way to keep the universe static. So it's kind of ironic that we think that lambda is actually what's making the universe accelerate. Yes, that's right. So this is this in the context of Einstein's theory of general relativity, what this lambda could represent. Of course, this is a like repulsive force, and this could, we'd like to. It's very difficult to understand exactly what lambda is. It's not really satisfying to think it's just some number that we're just stuck with. It's some just constant factor. That's not really intellectually satisfying. What you'd like to do is you'd like to associate it with the energy density of the vacuum. But when you try to do that in quantum mechanics, you don't get the right value of lambda out. It's very different, off by over 100 orders of magnitude. And so we don't really know what lambda is. This is an active area of research. Dark matter is a little easier. We got some good ideas about dark matter. So dark matter is it behaves gravitationally like the regular stuff we know about, protons and neutrons. Even though we haven't detected it, it doesn't interact with regular matter the way protons and neutrons interact. So we haven't detected it directly, but we've measured the motions of stars, we've detected it indirectly, and we've measured the cosmic microwave background, and we've detected it indirectly there. You need dark matter in order to produce the pattern of microwave radiation that we see in the sky. okay, that fills the universe. You need that dark matter there, or you don't get the fluctuations that you see in that pattern. And so with dark matter, there's a lot of good ideas for different particles that it could be, and we just would like the satisfaction of detecting it. With dark energy, and there are plenty of different theories about that, particle-based theories, supersymmetric theories, lots of different good ideas about what dark matter is. With dark energy, we're in a little bit more of a tough situation, which makes it a really exciting area of research because, wow, that seems like big low-hanging fruit, 75% of the energy density, but it's pretty hard. And so it's part of what we're struggling with. There are ideas that dark matter could form black holes. There are notions of that. And if you had the dark matter density high enough, you could get a dark, you could get a black hole that way. So we don't know what the dark matter is, but if you had dark matter that was near the event horizon of a black hole, then gravitationally it would be attracted to it.
And we'll have an advertisement in 2 weeks. Bob Kirshner will be giving a talk about dark energy, so you get a chance to learn a lot more about that in a couple weeks. Let's go up there, gentlemen. There.
I think I remember reading about a year ago that a black hole in our Milky Way, Sagittarius A star,
That's right.
was getting ready to feed.
Oh, yeah. Oh, yeah, this was a big deal. We got all excited. Yeah, that's right. So, because it didn't eat anything. Okay. This is G2. So you had a gas cloud on what looked like a Keplerian orbit around the black hole. Now, if you just have regular gas that's not in any kind of bound object, it just gets like ripped up, or it just does some random stuff, or not random, but it does some hydrodynamic stuff. It doesn't go on Keplerian orbits around anything. So there were some of us who did not think that it was going to feed the black hole based on this. But it was pretty exciting because we didn't really know what this object was. And it could have been just a gas cloud sort of going into the black hole, in which case it would have, there would have been some emission associated with that feeding event. But in fact, G2 survived, and so it's most likely a star on an orbit very near the black hole.
So if I get this right, black holes are protrusions of 3D space into 4D space. So if you think of it, if you go back to 2D, because I like going down dimensions, it makes it easier to visualize. If you have this, you can basically chop it up into slices to see what some two-dimensional thing would see if you could actually see while it was in a black hole. So basically, if you throw something, could something actually, if somebody goes in there, would it be still actually in 3D space?
This is the information paradox. You've hit upon it, my friend. Absolutely. So it's not clear what happens to something when it goes in a black hole. So for a long time, we had this idea that if you went into the black hole, right, feet first, that you would get spaghettified. Right? And the reason is because at your feet, the gravity would be so much stronger than at your head that it would just stretch you apart. Okay? But now we think that, as you remember when we're doing those slices, when we're getting down in there, space-time is getting more and more curved itself. So in fact, you're getting crushed in on yourself. And we have, some good string theoretic ideas about what actually happens to you, what happens to the information that you are. And we don't, there's famous debate about this. This is called the information paradox. Does information actually get destroyed in a black hole or not? And string theorists think that it does not, in fact, get destroyed. And so that's that alternate view of black holes that I was referring to earlier, but I didn't get a chance to talk to you tonight. But I just want to encourage you to keep thinking that way, because you've got an excellent mind, young man.
Now, as I understand it, black holes can rotate, yet they have no surface. So
Right.
It's a virtual point?
Well, so yeah, it's a virtual point. So it's just so again, this is a mathematical construct, right? So the actual space-time can be rotating, right? And so that's what, and so then it slightly changes the equations. It makes them more complicated once you add the rotation in, but then, you can handle it. In fact, we can do simulations of this rotating. It's what's called the Kerr metric as opposed to the Schwarzschild metric.
Would it not emit any energy?
If a black hole did not rotate? So
Is that theoretically possible?
when you say emit energy, are you referring to the accretion?
X-rays come off a black hole.
Yeah, so even even a Schwarzschild black hole, if it's accreting material, so what you're seeing is the innermost stable orbit of that gas that's crashing into itself. So that radiation is, there's other radiation called Hawking radiation, which is coming from the black hole. It can evaporate them. But the radiation that I was talking about is from this accretion disk, which is happening at much larger scales. And so, in fact, you can still have an accretion disk around a non-rotating black hole. And we don't know, we'd love to measure the spins of black holes. And in fact, one way to do that is to try to look at the detailed shape of the X-ray emission. As you get closer into the black hole, the energies that are emitted are higher and higher. So the higher energy you can go to, the closer in you can see. And by looking at the detailed shape of, one particular line that everybody likes is called the iron K alpha line, because it's a line that could get distorted as a result of that spin.
The young gentleman back there.
I was wondering how you said that you have no idea that you don't actually know how supermassive black holes are made. Do you have any theories at all, even if they are far-fetched?
Yes. Oh, yes. Oh, yes. We have lots of theories, ranging from not so far-fetched to like maybe pretty good to.
Which one do you think is the most plausible?
Well, now, sir. Okay. So one thing that we can do, so what's hard about growing these big black holes, these big supermassive black holes, is that we see them when the universe is really, really young. So we see them when the universe hasn't had that much time to really, get a lot of the mechanisms that we'd like going. Some people think that you just have, sort of a sort of massive star cluster collapse or something like this that will give you something that's around 1,000 solar masses. Once you can get to 1,000 solar masses, then we're in business. And the theory I think is most plausible is mine, which is when you go from 1,000 solar masses to something like 1 billion solar masses, the way you do that is by eating stars. You crush up stars in an accretion disk. And in fact, it's not just mine. It's other people have come up with these ideas, but I think it's a good one, and I've worked on it. And so once you can get to 1,000 solar masses, then you're in business, and it's really kind of getting from this sort of stellar mass black hole, and you can collide black holes together and maybe get up to that 100 solar masses, but then getting to that 1,000 to 10,000, that's the tricky part. And so I think the problem is we just haven't found those objects to really test these theories. So right now, it's anybody's game, I think. There are some crazy theories, which I think are not plausible, but I won't pollute your mind with them.
I missed a point in your lecture.
Were you coming for this?
How can, as the matter accretes around the event horizon, how can that be brighter than the entire galaxy?
So this, this innermost stable. So okay, you've got this gas accreting into this system, and the gravitational force of that black hole is extremely high, right? So it has to lose a lot of energy to get to that innermost stable orbit. Okay, and that's how you get these very, very large luminosities, because you have all of this matter that has to lose all of its. First of all, you have E equals mc squared, right? So you have a lot of energy associated with that sort of conversion from that gas, that gaseous material to the mass of the black hole. And so that's a big, big number that sort of that comes out, right? Because c is a big number, and you square it and get a really big number, and that's sort of consistent with the numbers you see when you make those observations. And in fact, you can do better than that, not just the total energy, but you can actually look at the distribution of that energy in frequency space, and you find that that actually matches our observations of these objects in frequency space pretty well. But they're still puzzles. I would say this is still, it's relatively early days. I mean, think about, even though we've been observing, first of all, we've only been observing these systems for 100 years, and we've only really kind of understood what they are for, of order 50. And so I would say, in the sort of scientific timescale, that's pretty short.
Thank you. A two-part question. One, the supermassive black hole at the center of our universe, does it define the center of our universe?
No. It's just the center of our galaxy. So it could have been off-center, right? So it happens that the radio emission that you see, it happens that it actually corresponds, and those infrared stars that are going by, that dynamical center actually corresponds to the center of our galaxy. But it could have been slightly offset, because our galaxy has a lot of stars and dark matter that, the gravity of the black hole is pretty insignificant compared to the gravity of the whole galaxy.
So do we see the black holes as singularities stationary, or are they moving within the galaxy?
So the stellar mass black holes are moving within the galaxies. The supermassive black holes can also be moving within the galaxies. There are models for these intermediate mass black holes that we haven't found yet. Those would be moving in star clusters probably in the galaxy. So no, they do not have to be stationary. As well as we've measured so far, our supermassive black hole is at the actual dead center of the Milky Way, to the extent that we can measure that. But in principle, if another we're going to collide with Andromeda, for example, and there'll be a period of time during that collision when the black holes will not be at the center, although they very quickly will find a new dynamical center and merge there.
So one more question, and then this gentleman here.
What would you expect to see if two black holes collided with one another?
That's a great question. So the most important thing that we could possibly see is the gravitational radiation associated with that. So if you have two black holes, two supermassive black holes, or even two stellar mass black holes colliding, that'll give a specific signature in gravitational waves that we would hope to detect either with something like LIGO or with future gravitational wave experiments. Certainly you would hope to detect that. If they actually have, we're not sure what the electromagnetic counterpart to that collision would look like. It depends on the gas, because the space-time, the collision of the two singularities gives off these gravitational waves. But what does the gas around those things look like? I mean, that should be a pretty incredible event. And in fact, one of our postdocs, Tony Pyra, who I think is in the audience, he actually works on the electromagnetic counterparts to these collisions. And so, I would say it's still, I would say the most exciting thing we could see probably is the gravitational waves, but we'd hope to be able to localize those waves with some type of a cosmic explosion in the gas that might be associated with those.
So I know we have more questions. If you have them, please come up. I'm sure June will be happy to answer them. Let's thank her again.
They weren't in the textbook. And here it's like they're around the corner almost. Not quite. Well, maybe it's been all over since I thought. Maybe that's right.